Yeah, thanks for the introduction. So this is, I think we're going to talk about post-quantum zero knowledge proofs for accumulators with applications to ring signatures from Symmetric-Key primitives. This is a set joint work with David Werner and Daniel Zimmer. So what are ring signatures? This is a privacy-enhancing primitive where one can sign a message on behalf of an ad hoc group, which is the so-called ring. And the signature only attests that one of the members signed this message, but the signer itself stays anonymous within the ring. So, other than that, we have the signature scheme with this additional privacy property. So the question is, how can we construct ring signatures in a post-quantum setting? There are already some existing constructions which are already 10 years old, which the first one is Maker and all, which used coding construction from coding theory. And then there's later from last year multivariate-based constructions by Mohammed et al. But these have the drawback that the signature sizes are linear in the number of ring members. The first sublinear ring signature is by Libya or from 2 years ago from Eurogrid, which is a lattice-based construction. But this ring signature scheme is based on a generic accumulator-based approach, which is from Doris et al. So the question is now, can we build such a ring signature scheme also only from Symmetric-Key primitives, since the previous ones were all from structured hardness assumptions? So let's take a look at this generic approach from Dolis. And here the idea is to first start with the set of public keys, then one computes a compact representation of these keys in accumulator. Then one proves knowledge of a secret key that corresponds to one of the public keys, and in this proof one incorporates the message. So, of course, in the Symmetric-Key setting, one of the accumulators that we have are Merkle trees. So the idea is that in the leaf nodes we have all the public keys of the users, and then, as usual for Merkle tree, we compute the hashes of the underlying nodes, and at each leaf node we have a secret key associated to a public key. For this Merkle tree, the first issue here is how can we construct a membership proof in zero knowledge. So a naive approach would reveal the path that we take through the tree. We just do it as usually with a Merkle tree, and so we would leak the identity of the signer. Then one could take another approach where we prove as a disjunction simply all possible paths, but this would require a proof for each path, and so we end up with again with signature sizes that are linear in the number of ring members, and this is what we want to avoid. In the work by Dolis et al., they use a commutative hash function where we simply have some kind of commutativity in the inputs of the hash function. So the hash of AI, BI is the same as the inputs reversed, and then we can construct these proofs without revealing the YI, the AIs, and the BIs. And so the path through the Merkle trees. But this is not directly possible in a symmetric setting, so we have somehow work around this issue. And so our idea is here, we want to emulate this commutativity, and we do this by using a disjunctive statement at each level of the tree. So we prove in the statement that you see here at the bottom that the current value is either the hash value of AI and BI or the hash of BI and AI. So, and then we already end up with a ring signature scheme. So we accumulate all the public keys in the Merkle tree accumulator. We prove the knowledge of the secret key corresponding to one of the public keys, and then obtain the ring signature scheme. So the unforgeability of such a scheme follows simply from the properties of the Merkle tree, and for the relation between the secret keys and the public keys, we use a one-way function. And then we also require simulation sound extractability from the proof system, to get unforgeability. When we then come to the instantiation, which is based on Symmetric-Key++, which is a proof system for arithmetic circuits, we have proved in this paper that Symmetric-Key++, when combined with the Fourier transform, is actually provides simulation sound extractability. When considering the post-quantum variant with the Unruh transform, this was already shown before. Okay, and the anonymity we simply get from the zero knowledge property of the proof system. Alright, so how can we instantiate this? So we here can use Symmetric-Key++. In Symmetric-Key++, we can obtain proofs for any circuit, but the proof sizes depend on the number of AND gates that we have in the circuit. So we are looking for primitives and hash functions that have a low number of AND gates. So one of the candidates here is C, and we can use it to both instantiate the one-way function that we use to show the relation between the secret key and the public key, and we can also use C to build the hash function and plugging in C in the spawn tree. And then we can give first results and estimations for signature sizes in the number of ring for a certain number of ring members, and for ring sizes from 2 to the 5 members with around 2 megabytes in the random oracle model, and in the quantum random oracle model we then are at around 3 megabytes. When increasing the ring size, the numbers increase in logarithmic way, and for larger sizes, with 2 to the 20 members, we are at around 8 megabyte and 11 megabyte in the post-quantum setting. So this is quite large. And so the question is, can we do a little better? And the answer is yes. And so what we look at now is how can we instantiate the disjunction a little bit better. And so what we look here as a component here is a multiplexer. So this is, if we consider that as one component in a circuit, we have 3 input wires and one of the wires is a selection bit which just switches the output from the first to the first input wire or to the second input wire. So we can use this to simply get this disjunctive property in our statement. So when we have, if you recall the statement, we have once the hash function with A as first argument and B as the second argument, and then reversed. So here we have these 2 hash functions, hash function evaluations where we just had these 2 versions, and then we use the multiplexer to switch between the first version or the second version, depending on where we are in the tree. But this is still not better. We still have 2 hash function evaluations, which are the most expensive part of of the proof and the computation. We switch those two parts around and use the multiplexers to switch the inputs depending on which case we want. And this allows us to get rid of one hash function evaluation and reduce computation time and also, more importantly, the signature seeds. So now we have here two multiplexers. Each of them requires, if implemented straightforwardly, one AND gate per output bit. But one can observe here that each of these two multiplexers performs one AND gate in the same way as the other, so we can use some intermediate values here and have then multiplexers. Those two multiplexers can be represented with only one AND gate. So, and as we get rid of one hash function evaluation, we then obtain also already a lot smaller signature sizes. And so we can save one hash function evaluation, but instead use one multiplexer that slightly increases the signature size, but since we get rid of one hash function evaluation, we can still reduce the signatures by a factor of 2. And now, the sizes are already looking quite a bit better, and we're down to 1 megabyte for the smaller cases and to 4 megabyte for the larger signature sizes. So this is an important first step towards post-quantum privacy enhancing primitives that we can, where we show that we can build them from symmetric primitives alone, where we use post-quantum accumulators and zero-knowledge proofs. And this technique that we used here is also very flexible, in the sense that Monet et al. Recently showed that a similar technique can be used to construct dynamic proof signatures also in a post-quantum setting. And this is also one of the important privacy preserving primitives. The signature size optimizations that we showed here also directly apply to Monet et al.'s work, and which also reduces the signature sizes there. Since they also have to evaluate two hash functions, and with the same trick we can also reduce their signatures by half the size. And so in this work we also require hash functions with low multiplicative complexity, and this opens up new research possibilities in this area to find better hash functions with in regard to this metric. The full version is available on ePrint, and we'll also include the updates to the signature size estimations and the optimizations there soon. So, thank you for your attention. I'm happy to answer questions.